Hello. In this video, we are going to calculate the speed, the velocity, of ejected electrons if we shine blue light with a wavelength of 475 nanometers on cesium metal. So the metal we're going to use is cesium. So the first thing that we want to do is to calculate the frequency of the blue light. And recall that the frequency is equal to the speed of light divided by the wavelength. The speed of light is a constant, 2.9979 times 10 to the 8 meters per second. And we know that our specific blue light in this situation is going to be 475 times 10 to the minus 9 meters, or using the trick that we've used before, you can write this as 4.75 times 10 to the minus 7 meters. So if we continue with this calculation, we see that the frequency is 0.631 times 10 to the 15th inverse seconds, also known as hertz. And we recall that the frequencies of visible light are on the order of 10 to the 14th and 10 to the 15th inverse seconds. So it's a nice double check that we have a reasonable answer. And recall that we know from Einstein that light can act as individual particles, and that the energy of those particular particles is equal to h times nu. H is Planck's constant, so that's our 6.626 times 10 to the minus 34 joule seconds. And we've just determined the frequency to be 0.631 times 10 to the 15th inverse seconds. We do a quick double check. We notice that our units of seconds and inverse seconds are going to cancel. So we will get an answer in terms of joules, which is the proper units of energy. So continuing our calculation, we see that each of the photons of the blue light that strike our cesium metal have exactly the same energy of 4.182 times 10 to the minus 19 joules. Now, for a point of comparison, we need to know the work function for the cesium metal. In other words, we need to know how much energy it takes to actually remove an electron from cesium metal. So this symbol we use for this. And very often, the units that are given for the work function are electron volts. So for cesium, the work function is 2.1 electron volts. Now the electron volt is not an SI unit, but it's a very commonly used unit by material scientists. So now 1 electron volt is equal to 1.602 times 10 to the minus 19 joules. So we can do a unit conversion here to actually convert the work function into more convenient units of joules. So we notice if we do this, that the units of electron volts are going to cancel, and we'll be left with an answer in terms of joules, which is what we want for the work function. So once we do that, we determine that the work function for cesium metal is 3.364 times 10 to the minus 19 joules. So we definitely want to do a quick comparison here of the value of the work function, which is 3.364, versus the energy of the photon, which is 4.182. We know from the photoelectric effect that the energy of the photon has to be at least equal to the energy of the work function. Otherwise, we won't kick out any electrons at all. And since we see that the energy of the photon is considerably larger than the work function, we actually will eject electrons, so we can proceed to the second part of our calculation to determine exactly what the velocity of those ejected electrons is going to be. So now we proceed to subtract the work function from the energy of the individual photon. And this particular difference is actually going to give us the kinetic energy of the ejected electrons. And we notice this is a value of 0.8178 times 10 to the minus 19 joules. And we notice this is a positive value. If we do this calculation and we determine that the kinetic energy is negative, that doesn't mean we have an electron with negative kinetic energy. It means that no electrons are going to be ejected at all. So now, to simplify, we want to solve for the velocity. So first step is to simply multiply each side of the equation by 2. So we get that mv squared is equal to 1.6356 times 10 to the minus 19 joules. And now we want to divide each side of the equation by the mass of the electron. And the mass of the electron is 9.11 times 10 to the minus 31 kilograms. The result of this calculation gives us the value for the velocity squared, which is 0.1488 times 10 to the 12th meters squared per second squared. Be sure to convert the units of joules to kilogram meters squared per second squared. The kilograms will cancel and we'll be left with meters squared per second squared. To simplify this calculation just a little bit, we can multiply the left by 10 to the second power and divide the right hand side by 10 to the second power. So we simply shift a decimal point to get 14.88 times 10 to the 10th meters squared per second squared. And now the only thing left to do is to take the square root of each side. So we take the square root of the left-hand side and the square root of the right-hand side. We'll be left with the velocity. So this is the velocity of each ejected electron. And we determine that's going to be 3.85 times 10 to the 5th meters per second. We want to do a very quick reasonableness check on this because we recall that the speed of light is just about 3 times 10 to the 8th meters per second. If this velocity were to be an appreciable percentage of the speed of light, we would have to use a completely different equation because then relativistic effects and the special theory of relativity would become important. But since this is much smaller than even 1% of the speed of light, this is a reasonable answer. And this is the velocity of each electron that's going to be ejected from our cesium metal when we shine light with a wavelength of 475 nanometers onto it. I thank you very much for your attention. Have a good one.